The other method that we're going to look at for approximating a root or finding where a graph would cut the x-axis is called Newton's method. Now, Newton's method does include some calculus, fairly simple in that we just find the derivative. So it's probably suitable that it's here in a further calculus chapter. Now, to understand Newton's method is really easy. It's based on really easy concepts. There is a formula, however, and if your preference is, again, just to learn a formula, and the good thing is this formula is on your reference sheet, that's the formula. You can see it's here that the calculus comes in. We're going to find the derivative. I'll spend a little bit of time talking about where this formula comes from because it's not difficult and it may help you in other situations just to be able to work through some really easy concepts. I'm just going to go to a blank page so I can demonstrate it. If you prefer not to know the background to the formula, you might just fast forward till you come back and see this page. So let's say we've got this situation where obviously this is the root of the function, but let's say the best we could do is we know that the root is somewhere near this x value. Now that is a major assumption, that you've got to, the first value that you start with has to be fairly close to the actual root. Now in most questions that will be given, so you don't have to worry too much about that. Now from there, Newton's method is based on thinking about drawing a tangent to the curve at this point, where we've got x value, and if this is some function in x, the y value is the function in x. So that's just the coordinates of this point here. So thinking about the point on the curve above where we think the root is near to. And very simply, from there, think about drawing a tangent. What do you notice about the tangent? If we draw a tangent there, what do you notice about this point? Hopefully you can see that, yeah, at that point, we're actually getting closer to the actual real root. So this point here, which I'm going to call x1, is closer than what x was. But if I go through the same process and I think about here, so remember it was at x, at my first approximation, I considered the tangent at the point x. Then I've discovered a new point, a better point, because it's closer. But if I go through the same process and I look at, say, the tangent now at this closer point, what do you notice about the tangent now? If I draw the tangent in, then that point there, which I'm now going to call x2, is even closer again to the real root. Now, that's all Newton's method is based on, finding these points where the tangent cuts the x-axis. Now, the thing that we know about along the x-axis is that y is equal to 0. We know how to get the equation of a tangent. We will need the equation of a tangent, and we learnt that very early on. And in that equation, we then let y be 0, so we can find x. We can find the actual x value where the y is equal to 0 on that tangent. That then gives me my closer approximation. Go through the process again. Now, that formula you saw back on the other page comes from those steps. Let's have a think about here. Let's have a think about getting the equation of the first tangent, the red tangent. So we know that the equation of a tangent is the equation of a straight line. It passes, so it's of the form y minus y1 is m times x minus x1, because it's a tangent is a straight line. So its equation would be, what was y1? y1 was f of x. What is the gradient of that line? We know the gradient of that line is the derivative. Now, remember I said the derivative does come into Newton's method? Here's where and why it comes in. X is the x of our equation, but what was x1? Oh, actually that's going to be really confusing, isn't it? I'll just call that for now this x. And knowing that these are not the same. These two things are not the same. Now, so that's got the equation. To find x1, I'm going to put y equal to 0. Y is equal to 0. So we'll have 0, we'll have minus f of x is equal to f dash x, x minus, I'll call it the black x for now. Now, if we just want to make this x, this is the one we're trying to find, this x1. Make that the subject. So divide both sides by f dash x, and we'll get our x minus our first, remember that was our first estimate for the root. Now we're almost there. We'll bring that x, bring this across to make this new, this is the one we want. This is going to be this one. We want to make that the subject because that is the better approximation. That's the closer one. So if we bring that first estimate across and subtract the function value at that spot and the gradient at that spot x, then we get our new x, which I'm in there going to call x1. Then that's basically the formula. If I jump back to this other page, you can see our better approximation is our first approximation minus the function value at that spot over the gradient at that spot. And this diagram is a little bit confusing because we now go to a's instead of x's. So that's why I like to do it on a separate document. Let me go back to that one. We could work through here, and maybe in the red it'll be easier. So what do we know here at x1? We know that this point here, it would be called x1 and the function at x1. We would have the gradient at point x1. So the equation for the green, let me pick up green, would be the equation of the tangent, y minus the function at x1 is equal to the gradient at x1, f dash x1, x minus x1. So y minus y1 is m times x minus x1. Now, we're going to find x2, that's what this one's going to be eventually, x2, the x value where this tangent cuts the y-axis, this goes to 0, so we just have minus the function value at x is the gradient, and this becomes our x2 eventually. And divide both sides by f dash x1 is x minus x1. To find this new and closer and better, and we'll call it x2, bring that x1 across, it becomes a positive, and subtract the y value over the gradient value, and they're at x1. Now, that might look a bit close, a bit more like the equation on the sheet. Let's have a look. Yes, that x2 was x1 minus the function value at x1 over the derivative. That's where it comes from. I don't think that's too difficult really to understand. The good thing is the formulas on the sheet. So to find a better, closer approximation, which is called, in this case, x2, use the previous approximation for the root, the x value minus the y value at that spot over the gradient at that x value. Yeah, the y value on the curve over the gradient of the tangent at that point on the curve. I'll stop the video there and do an example in the next video.